derivations in fields where the source is, let us suppose there is a source which is a straight line. Whenever I want to determine the field of a line source, maybe line charge or long straight conductor, at any point, definitely the field of a long straight conductor will be cylindrically symmetric, in the sense at each and every point on the cylinder, the magnitude of the field is same and the form of the field is same. At any point on this cylinder, let us say this point, I want to determine the field because of this line. When I want to determine the field because of this particular line source, I will divide this line into so many very small line charges at any z. Element of length dz we call it. Whenever I want to talk about the field at a given point because of the entire line, I have to divide that line into so many infinitesimally small line sources. And the field is defined if I know the vector from the source to the point of observation. If this distance is z from the reference, the vector is what? Carefully see this. I have to travel in this direction, produce minus z az, correct? Travel away from z axis, produce r arrow, minus z az, r arrow. This vector is no r arrow minus z az. Very, very important, very, very important vector. Because whenever I want to determine the field at a particular point, I need to define the vector from a general point on the source to the point of interest. Only if I can define this vector, I will be able to talk about the field at that particular point because of the point source selected at a general point on the source. And listen carefully. For all the points on this circle, which are there on the cylinder, the vector is same, correct? Hey, what is the vector from this point to this point? Again, minus z az, moving away from it, right? Throw arrow. Same. What is the vector from that source to this point? Minus z az. Come down. Again, go along a radial line to this. So, this is the vector from the source to any point on this circle. For any phi, we'll say. That point will come onto that phi constant plane, and then I can define a vector. Minus z az plus rho plus r arrow. Towards that point, I will go from directly along a radial line. Please check it once. The magnitude of which is root of r square plus z square back, because they are two mutually perpendicular lines. One is vertical, another is horizontal radial line. One more. Again, very important also for us when it actually comes to magnetic fields. And we talk about the same thing in the electric fields also, for the sake of mathematical extension of the field. If I have a circular ring as a source, ring charge, or a current loop, it can be a circular loop carrying the current, or a circular conductor having the charge on it. Definitely it will be uniformly charged, no doubt about it. If some charge is put onto the circular conductor, the charge will uniformly spread onto the circle. I want to determine the field, assuming that this plane is there, an XY plane. I want to determine the field on its axis at any point. Whenever I talk about this point, I say H is the point. H is the distance along this Z axis. Again, whenever I want to determine the field at this point P due to this circular source, I will divide it into so many small elements. I need to first of all determine or get the vector from any general point. What is general point? At any phi there can be, because this is a circle of radius A. Any general point is what? A point at an angle of phi. Phi is 0 to 2 pi. At any phi, I have a small element. From this, I should be in a position to define the vector to the point of observation. What is this? I have to come back horizontally. Correct? Produce minus A rho. Then go up to produce HAZ. From this point, also same, minus A rho plus HAZ. The vector from any point on the circle basically given by phi. Phi is equal to constant on the circle to P is minus A rho plus H AZ. Please check it. These two are very, very, very important vectors for us in electromagnetic fields. If I want to study electromagnetic fields as such, I also require the derivations, at least few derivations to support our discussion required for the components as well as mathematics, because of which I will be using them. I want you to check whether this is clear or not. They should be there on constant phi plane. Only then I can define a vector. If one point is there on one phi plane, another point is there on another phi plane, I cannot do it. Or from any point in the space to any point on the z-axis, I can define a vector. That's what he's telling you. Or from any point on the z-axis to any point in the space, I can define a vector with two components. Check for complete clarity. Ask if I have any doubt. I'll say normally at any phi, I'll say in this particular case, consider an element at any value of z, small z. Then integrate it with respect. Such elements are taken from minus infinity to plus infinity in z because the source is dz. Integrate it z limits. Here, from consider a source at any phi. A d phi is the length of it. dl. Rho l into a d phi or I a d phi if it is a current element ideal at that particular phi. D phi will come. The length is a d phi. For that from that source point, they will determine the field at that. Now I want to determine the total field, integrate it over entire phi from 0 to 2 pi. While integrating, because I can only add the vectors in the same direction by using integration. Integration is a dummy thing actually. I should use integration provided in the vectors I should use integration only if the vector is same in the direction everywhere. X component can be integrated, Y component can be integrated separately. Just like that, vectors cannot be integrated. Integration is for each component. There are some cases where even though it appears to be arrow, the same component, it is zero effectively. And we should have the physical understanding of the coordinate system to say that. Derivations are very simple in electromagnetics. Subject is very easy. Only thing is, you should be in a position to visualize the coordinate systems and then know what really is happening. Having the picture of that particular field, you should derive. Blindly, you cannot understand the derivation. Yes. Some critical things that we have to tell, even though they are not there in our subject, I will develop them and I use them also for my subjects. Check it. Is it clear? These two cases are extremely important. Okay, next. We saw dl bar in Cartesian coordinate system. What is that? Change x by dx without changing y and z. Dx ax at any point. At any point only is the general definition for us. Plus change y by dy without changing any other coordinate dy ay. Plus change only z by dz. Dz az. Was the differential vector in Cartesian coordinate system, because of which our differential length dl was what? Root of dx square plus dy square plus dz square. In this coordinate system, it is keeping phi and z constant, change rho by d rho, a rho, plus keeping rho and z constant, change phi by d phi, move along a circle of radius rho. on z is equal to constant plane. By d phi producing a arc of length rho d phi. Very, very important, very, very important to know this. A phi plus change z without changing rho and phi dz az. It's just the third component that we are getting now. D rho a rho plus rho d phi a phi plus dz. Later on, when you go to divergence, curl and all, gradient, divergence, Laplacian and curl, we can derive them in Cartesian coordinate system. But in fields, most of the time, we will use them in cylindrical or spherical coordinate system. And it becomes really very difficult because there are approximations, lengthy procedures. To talk about the divergence curl of the vectors in these curvilinear coordinate systems called as cylindrical and spherical coordinate systems. Then we give the expression in terms of h1, h2, h3 in the universal coordinate system. If you know what is h1, what is h2, what is h3, and what are the coordinates in that particular coordinate system, that universal formula will give me everything. That I have to remember. You have to remember because derivation is with approximations. If there are no approximations, I will tell you to derive it. I will develop the derivation procedure. But if there are approximations, it is really difficult for us to remember the approximations to derive it. I will not do it. H1, H2, H3 basically are defined from differential vectors because of which you should have understood this. Differential vectors in all the coordinate systems you should know properly. This is in cylindrical coordinate system where dl is equal to what now? Root of d rho squared plus rho squared d phi squared at any rho phi z plus dz squared. Same thing were there with x and y. Z has come as an extra component in both the coordinates now. Check it. DL bar and differential length. Careful. DS rho means what? Differential surface element on any constant rho surface is what? Cylinder of radius rho. At any point on the cylinder of radius rho, it's a surface. You can define a differential surface element by creating a rectangle with one side as what? One side obtained by varying phi by d phi, rho d phi. You have to see these two components will come into picture. Into dz. One side is rho d phi. Another side that I can produce is by varying other component z. Please keep looking at DL bar. Any DL bar on constant rho surface is what? This is because DL bar on constant rho surface can be only rho d phi a phi plus dz az. Correct only, no? Because on constant rho surface, I cannot change rho and produce d rho. Rho is constant. The product of these two components will give me this, right? Rho d phi dz. ds rho. dl rho bar. What is ds rho bar? What is normal to this? Rho is equal to constant surface here, which is rho d phi dz depending upon the direction, plus or minus a rho. I defined it like dsx is what? dy dz. dsx bar is dy dz plus or minus ax. Similarly, dl phi bar is what? On phi is equal to constant plane. I can only change rho. D rho a rho. And z. dz az. These are the two sides d rho dz. Straight away, they are distances, because of which ds phi is equal to d rho dz and then ds phi bar is equal to d rho dz plus or minus a phi at that particular point. Phi is equal to constant plane it is. Hope you are continuously understanding here. Check next. dsz is the same as the circular plane that we were talking about, right? dsz bar, dl z bar is what? D rho a rho. I can change at any point. And rho d phi a phi. Rho is a constant at that point. Rho phi z. Change phi by d phi, produce a length, the rho d phi. dl it is, because of which each component should be ultimately length. D phi should be in radian. dsz is rho d rho d phi. D rho is one component, rho d phi is the other component. I'll write it as rho d rho d phi. And then dsz bar is equal to rho d rho d phi plus or minus az, depending upon which component I'm considering. Outward, inward in the first case, right? Like no, downward or upwards, z case, last case. In the clockwise direction or anti-clockwise, phi. These are the differential surface elements that come into picture in surface area calculations, right? And the surface integrals. Next, finally, in this coordinate system, what is differential volume? Differential volume is what? At any point in the space, I should be in a position to independently vary all of them. That is actually the differential vector d rho, a rho, rho d phi, a phi, dou z, because of which differential volume is what? The product of all the components, d rho into rho d phi into dz. So, rho d rho d phi dz is the differential volume element. Check it. Just for the sake of talking about it, in cylindrical coordinate system, if I want to calculate the curved surface area of cylinder of radius A, curved surface area of cylinder of radius A and length L. Normally what we do is, we open this cylinder, it will be a rectangular surface of height L. Open it, it is 2 pi A. We have to derive this 2 pi also now. So the area is 2 pi A into L. Before that, listen carefully. Circumference of a circle of radius A is 2 pi A, correct? How did I get it? On this circle, assuming it to be there in xy plane, because I want to determine the area, where it is doesn't matter for me, as circumference. I will consider this with its center at origin. I want to determine the length of this circle, total length. At any phi, what is dl is equal to a d phi? Do you agree? I can only change phi by d phi, producing an arc of length a d phi with phi in radian. Total length is what? Integral dl is equal to integral a d phi. I should select such differential elements at all values of phi from 0 to 2 pi, because of which it is 2 pi a. You know this. Now, carefully. I want to determine the curved surface area, not top and bottom circular discs. Circular disk area we calculated as pi a squared, we know that. Now I want to determine the surface area of this cylinder, just for the sake of knowing it. Seeing it rather. No, you know it. Now, on the cylinder, consider it to be there on z-axis from 0 to L. Z is equal to 0 to Z is equal to L. I will consider radius A. I know that ds rho on the cylindrical surface of radius A is what? A d phi dz, correct? On the cylindrical surface of any radius rho, it is rho d phi dz is the surface area, surface, elementary surface. I want to take integral ds rho, double integral it is, or surface integral equal to, because they are all independent, a d phi dz, phi from 0 to 2 pi, that's what I have to, at any z I have to go from circle, it is 0 to 2 pi, z from 0 to L. Definitely the first integral evaluates to 2 pi a. Integral 0 to L dz is equal to L, because of which it is 2 pi a L. Is the curved surface area of the cylinder of radius A and length L. Because it is a cylindrical coordinate system, I am talking about the full part also we can calculate. You know that. Only thing is I have to appropriately take the limits. What is the volume of the cylinder? Same cylinder. I want to know the volume. Volume is, we know that. It's pi r squared L. But I want to get it. Volume. with dv is equal, it is actually what? Volume integral of dv in the coordinate system. Volume integral is always triple integral. dv is equal to what? Rho d rho d phi dz. Rho goes from 0 to a because it is a cylinder of radius a only. Had to go full circle because of which phi goes from 0 to 2 pi. It is cylinder of length L going from Z is equal to 0 to L because of which it is 0 to L. When I evaluate this, it is rho squared a square by 2. When I evaluate this integral d phi 0 to 2 pi into 2 pi, when I evaluate final Z integral dz from 0 to L is L because which it is pi a squared L. Check it. This is the theory about cylindrical coordinate system that we require. Again, I don't think I have to talk about again aero.ax, aero.afy, same. Az is az only, right? To convert, if it is required somewhere practically, the vector in cylindrical coordinates to the vectors in Cartesian coordinates or vice versa rho and phi components to x and y components or x and y components to rho and phi components are obtained using the formula in circular coordinate system. Az is same in both. It goes into the other coordinates also as it is. Please check it. This is one of the most useful coordinate systems for us. You will see that many a time in fields you will be making use of this coordinate system. Relax for 10 minutes. We will quickly discuss the spherical coordinate system required for us to get into antennas. Okay, where naturally it is spherical coordinate system because it is a huge universe into which you send the signal using an antenna normally mounted on the surface of the earth, because of which it radiates into the upper hemisphere. Because it radiates into the upper hemisphere, which is the part of a sphere, the natural coordinate system for us to study antennas and wave propagation is spherical coordinates. So we should know that spherical coordinate system also.